Okay, in today's lesson, we're going to turn our attention to the study of powertrain elements. Gears, pulley drives, and sprockets are used all around us, and they're especially relevant to the understanding of how machines work. Recall seeing gears on your bicycle. Do you know how the bike gears work to move the bike forward? In today's lesson, we'll talk about how gears are used in machines such as clocks, bikes, and cars, and we'll even dive deeper into different arrangements of gears called gear trains and how they're useful for transferring energy from one part of a system to another by changing the speed, torque, and direction of a power source. These concepts are important for you to understand so that you are ready to tackle the upcoming engineering challenges throughout this section. Gears, pulley drives, and chain and sprocket systems are three powertrain elements that transfer energy through rotary motion. These three powertrain elements are used to change the speed, torque, and direction of a power source. In general, these powertrain elements are used for two main purposes: increasing speed or increasing force. In order to increase one of these, compromises must be made. For example, to increase the speed of a bicycle's wheels, the force applied to the pedals must be increased. Similarly, to increase the force on the wheels, the pedals must be turned faster. This technique is used when a rider is trying to climb a hill on a bike. Gears are commonly used in many systems, but they can most easily be recognized in everyday life in the cars we drive. Cars must make use of gears in order to transfer energy from the engine to the wheels efficiently and safely. An idling engine operates at about 1,000 RPMs, or revolutions per minute. If the engine was connected directly to the wheels, this would mean the car must be moving approximately 100 kilometers per hour. This means if a car's engine is turned on, it would immediately accelerate to this speed. When the engine moved into ranges with higher RPMs, around 7,000, the car would be going 840 kilometers per hour. Although this seems very fun, it's highly impractical. This is impractical due to the fact that a car requires a large amount of energy to get moving. So an engine trying to go full speed just as it started up wouldn't generate enough force to move the car. Therefore, the car makes use of gears and transmission, or alternatively, a gearbox, which starts off by using lower gears that generate more force in order to get the car moving, eventually moving up to higher gears that focus on speed. The same principle of gears applies to bicycles. Going uphill requires lower gears in order to supply more force to counter the force of gravity. And once the rider is back on flat land, they can switch to higher gears in order to generate more speed for their bicycle. A gear is essentially a wheel with teeth that meshes with another simple gear that is typically larger or smaller. When two or more gears are used in combination and are meshed together by their teeth, they form what is called a gear train. A gear train is a mechanism that is used for transmitting rotary motion and torque through interlocking teeth. Just like levers, there are different kinds of gears. Effort is applied at the driver gear, which causes the motion, and that motion is then transferred to the driven gear, where the driven gear can then move the load. When multiple gears are used in a gear system, they can make things easier to move. The teeth on two gears fit or mesh together by having the same size teeth, or diametral pitch, which allows for one gear to turn the other. In a simple two-gear system, when you rotate one of the gears clockwise, the other gear will rotate in the opposite direction, counterclockwise. But if you add a third gear to the middle of two gears, you create what is called an idler gear. The idler gear allows both the input and output gears to rotate in the same direction and helps add distance between the gears. As well as being able to change the direction of rotation, gears can also change the rate of rotation due to the fact that gears come in various sizes and types. But depending on the situation, one gear may work better than another. A gear with fewer teeth must rotate more times when it meshes with a gear that has more teeth. For this reason, the revolutions per minute, or RPMs, of a larger gear is always slower than the RPMs of the smaller gear, but it will have more torque than the smaller gear. Therefore, if the driver gear is larger than the driven gear, there will be an increase in the turning speed. This is called gearing up. Conversely, if a small driver gear is turning a large driven gear, This will slow down the turning speed, which is called gearing down. When it comes to torque, understand that torque is the rotational equivalence of linear force, and speed measures the distance covered in a unit of time. The relation between torque and speed are inversely proportional to each other. So if more torque would imply less speed and vice versa. Again, this is why bicyclists will regularly shift gears so often. By shifting gears, the bike can help them cover more ground faster or cover steeper ground slower. Or recall the difficulty of when riding your bike up a steep hill. If you shift to a lower gear, you are using a small gear to drive a larger gear, which will mean that you will need to apply less force to the pedals. But if you shift into a higher gear, you are now using a larger gear to turn a smaller gear, which is best if you want to cover the ground more quickly. It's also important to note that whenever gears are locked together on the same shaft, they will always turn in the same direction and at the same RPMs. Gears use the principle of mechanical advantage, which is the ratio of output force to input force of a system. For gears, though, the mechanical advantage is given by a gear ratio, which is the ratio of the final gear speed to the initial gear speed in a gear train. The gear ratio can be calculated 4 different ways. First, it can be found by finding the ratio of the number of teeth of the output gear divided by the number of teeth of the input gear. Second, it can be found by finding the ratio of the output gear's diameter to the input gear's diameter. Third, we can look at the ratio of the input gear's angular velocity to the output gear's angular velocity. And fourth, we can look at the ratio of torque from the output gear to the input gear. Therefore, in this example, you can see that the gear ratio of this gear train is 2. What this means is that the last gear in the train has a diameter of 2 times that of the first gear. With such a ratio, the input gear can be rotated with 2 times less force than its output by the final gear. But in exchange, it must be rotating 2 times faster than the final gear. In order to effectively work with these ratios, you must understand the following symbols. We're going to let N represent the number of teeth found on a particular gear. D is going to represent the diameter of that particular gear. The symbol for angular velocity is the Greek lowercase letter omega. The symbol for torque is going to be the Greek lowercase letter tau. And then notice that the subscripts in and out are simply used just to identify whether the characteristic of the gear refers to it as an input or as an output gear. Also make note of the rotation directions of each of the gears in this example. You can see here that I have 2 gears, one in red and one in blue. The red gear or smaller gear is my input gear, and the second gear in blue is my output gear. Notice that the diameter of the input gear is 2 inches. The diameter of the output gear is 4 inches. The driver gear is spinning at a rate of 40 RPMs, and the driven gear is spinning at a rate of 20 RPM. There are 2 types of gear trains that we will study in this course: simple gear trains and compound gear trains. In this image, we have a simple gear train connecting several gears together in a row, each gear having its own axle. So in this example, gear A is my driver gear. It is meshed together by gear B. Gear B is then meshed to gear C, and then gear C is meshed to gear D, which would be my output or driven gear. It says here, what is the gear ratio between gears A and B? Since they gave us the number of teeth of each of the gears, we can calculate the gear ratio by doing the number of teeth of my output gear divided by the number of teeth of my input gear. So for gears A and B, the output gear has 12 teeth and the input gear has 20 teeth. So if I take 12 teeth and divide it by 20 teeth, I get my gear ratio. What is the gear ratio between B and C? Same thing. Output gear is 5 teeth, input gear is 12 teeth, so 5 over 12. What is the gear ratio between gears C and D? 20 teeth over 5 teeth, which reduces down to a gear ratio of 4. Again, no units for gear ratios, similar to mechanical advantage. It's important to note that idler gears do not affect gear ratios. If you look at this example, what's the total gear train gear ratio? So I have 12 over 20 times 5 over 12 times 20 over 5. Notice the idler gears in the middle, both gears B and C, when you go to do the multiplication for the total gear ratio, those ratios in the middle would end up canceling out. So if gears A and D were directly connected to each other, the resulting gear ratio would just simply be 20 over 20, or simply a gear ratio of 1. If the last gear had 40 teeth, what would be the total gear ratio? I could simply just do 40 teeth divided by 20 teeth, or a gear ratio of 2. In this image, we have a compound gear train connecting gears that may share axles or shafts. In this case, you can see the two middle gears, gear B and C, are on the same shaft or axle. Two gears on the same shaft share the same torque and speed, although they are different sizes. This allows for more efficient manipulation of speed and torque throughout a system. Notice that the compound machine has a simple machine right in the middle, transferring energy and power from gear B to gear C as a wheel and axle system. This has a mechanical advantage of dE over dR, or in this case 40 over 20, which is 2. Being specific, gears are not simple machines, but simply identified as mechanisms. Simple machines and mechanisms are, by definition, devices which transform mechanical energy into mechanical energy. On the one hand, simple machines receive as an input a single force and give out an output as a single force. These machines use mechanical advantage in order to change the point of application of that force, its direction, and its magnitude. As we saw earlier in this unit, examples of simple machines are the lever, wheel and axle, pulley, inclined plane, wedge, and screw, and no more really. These 6 are the only simple machines that are classically considered since the Renaissance period. Mechanisms, on the other hand, are devices which receive a set of input forces and transform it into another set of output forces. Mechanisms are composed of several machines. As I mentioned earlier, gears are really a combination of a wheel and pulley. It is for these reasons that when designing a compound machine, each mechanism is either a simple machine or a powertrain element. The 6 simple machines contribute to mechanical advantage, which deals with forces and distances, and it is why it is considered to be the ratio of force, where that force is measured through cables or strings. And the 3 powertrain elements contribute to gear ratios, which deal more with speed and torque, and is why it is considered to be the ratio of rotation, where torque is measured about an axis of rotation. It's also important to note that both simple machines and mechanisms will always comply with the principle of conservation of energy. So to summarize, gear ratios are used similarly to mechanical advantage, but they apply torque instead of force. Think of it like this. A gear ratio is simply a multiplier of torque, and mechanical advantage is a multiplier of force. In order to calculate your output force, you would take your mechanical advantage and then multiply it by the input force. Likewise, in order to calculate your torque output, you would take your gear ratio and multiply it by the torque input. In a compound machine, the total mechanical advantage and gear ratios are just the product of their respective components. Mechanical advantage is only used to calculate forces, gear ratio is only used to calculate torques. As I mentioned, when designing a compound machine, each mechanism is either a simple machine or a powertrain element. The 6 simple machines contribute to mechanical advantage but not gear ratio. The 3 powertrain elements contribute gear ratio but not mechanical advantage. In this example of a compound machine, we have 3 mechanisms in series: a wheel and axle, a gear train, and another wheel and axle. An annotation of the compound machine has been provided with the picture in the slide. Notice the distances of the effort and resistance are both 4 inches, and gear 1 has 60 teeth and a radius of 1.5 inches, and gear 2 has 24 teeth and a radius of 0.6 inches. For mechanism number 1, the wheel and axle, you can see that the input force, Fe, on the black bar transfers force with mechanical advantage to the teeth of the purple gear. This wheel and axle system has a mechanical advantage of 2.67 and was found by taking the distance of my effort, 4 inches, and dividing it by the distance of my resistance, 1.5 inches. Since the black bar and the purple gear turn at the same angular speed, no gear ratio was contributed by this component. Therefore, the gear ratio is 1. For mechanism number 2, the purple gear then transfers the force to the blue gear. The force is transmitted teeth to teeth unchanged, therefore a mechanical advantage of 1. But the force on the blue gear is now at a different distance from its axis of rotation, causing a gear ratio that is not 1. Recall, to calculate gear ratio, it's the number of teeth of my output gear divided by the number of teeth of my input gear. So in this case, we have 24/60, or a gear ratio of 0.4. For mechanism number 3, the gear transfers force to the black bar at the output. Because the force of the blue teeth and the force of my resistance at the output are at different distances from the same axis, rotational equilibrium requires these forces to be different. This is a wheel and axle system with a mechanical advantage. Again, gear ratio is 1 since the bar and the blue gear rotate around their shared axis at the same rate. Therefore, the total mechanical advantage is the product of all the components' mechanical advantages. A mechanical advantage of component 2 was 1, which didn't change the product, since mechanism 2 was a powertrain element and not a simple machine. This overall mechanical advantage is used when comparing the force of my effort with the force of my resistance. So I have 2.67 times 0.15, and we get a total mechanical advantage from mechanism 1 and 3 of 0.4. The total gear ratio is the product of all components' gear ratios. In this example, only one gear ratio was not 1. You would use the total gear ratio if you wanted to find how many full revolutions of effort force is required to get one full revolution at the output. In this case, we had a gear ratio for gears 1 and 2 of 0.4. Moving on to another powertrain element, we're going to take a look at the belt and pulley systems. A belt and pulley system is a continuous band that wraps around the pulleys to transmit power. A driver pulley or input pulley powers one or more driven pulleys. The pulleys are connected by belts. The ratios are based on the relationship between the different pulleys. As you can see in the picture below, pulleys manipulate both torque and speed. If the output pulley is smaller than the input pulley, speed is gained, and consequently, less torque is available. If the output pulley is larger than the input pulley, torque is gained, but there will be less speed available. The ratios are the same for gears as they are for belt and pulley systems. The one exception is that there are no teeth to count, so you must rely on the diameter of each pulley. Another difference is that the two pulleys connected by a belt rotate in the same direction, whereas meshed gears will always rotate in opposite directions. Also, belt and pulley systems are able to slip. And finally, the other powertrain element that we're going to study is the chain and sprocket system. Notice that the chain and sprocket system looks similar to a pulley system. The difference is that a pulley uses a belt and a chain and sprocket system uses a chain to transmit power. Keep in mind also that sprockets and gears often get confused. Gears mesh directly with other gears, while sprockets uses chains to transfer the power between its sprockets. In order to calculate the gear ratio of a chain and sprocket system, again, we would use the same ratios. N out over N in, diameter out over diameter in, speed in over speed out, or torque out over torque in. And to conclude this lesson, I just wanted to kind of quickly talk about a comparison of advantages and disadvantages to using both the pulley system as well as the chain and sprocket system. So again, as a reminder, when using a pulley system, the method for transmitting force is going to be through a belt, whereas in a chain and sprocket system, that method of transmitting force would be through a chain. Some advantages of using a pulley system include it's quiet, no lubrication is needed, and it's relatively inexpensive. An advantage of using a sprocket system would be that there's no slippage and there's usually greater strength. The disadvantages of using a pulley system is that it can slip, and with the chain and sprocket system, it's usually noisy, has a higher cost, and often requires lubrication.